Hello, and welcome to Developing a Performance Face Mask by myself, Cole Nielsen, alongside Dana Boucher, Soham Joshi, and Max Kwan. Before we begin, I would like to thank Dr. Stephen Wereley for posing this initial research question to us and for providing additional mentorship throughout the project. The main research challenge this project intended to study was developing a face mask for use by people undergoing athletic activity during the COVID-19 pandemic. For many people, exercising with a face mask can be extremely difficult, and creating one that allows people to exercise normally while remaining safe would be incredibly valuable. We developed experimental procedures to test a number of masks currently available for purchase by consumers in order to develop an understanding for what makes a good athletic face mask. Additionally, we developed an on-paper design for what we think our face mask will look like, and compiled some information on what valuable features are for purchasing a face mask in order to exercise. When we were designing an experiment to test the efficacy of various face masks, the most important question was how do the various design features of a mask impact its performance? Our research team ultimately decided to test 5 different face masks due to their variety of design elements. These include a KN95 mask, the Under Armour Sport mask, the Athleta non-medical face mask, a standard surgical mask, and a standard cloth mask. Our experiment itself was designed with the assistance of Dr. Lindsay Bottoms from Hertfordshire University, who conducted a similar experiment seeing how wearing fencing masks would impact athletic performance. Our experiment was conducted with us researchers running at different speeds on a treadmill or stationary bike while measuring our heart rate and oxygen saturation levels. This was done at 3 speeds, a low speed of about 3 miles an hour, a medium speed of about 5 miles an hour, and a high speed of about 7 miles an hour. Now, let's go take a look at what the results were. Plotted here, we have the heart rate and oxygen saturation levels of the control without a mask and the Under Armour sports masks. The sport mask was chosen because it's a good representation of all 5 masks that were tested and can give you a good sense of what the general trends were. At low speeds, you can see that the heart rate is relatively similar between the control and wearing a mask. There's a noticeable jump in heart rate when wearing a mask at medium speed. However, once we get to the high speed runs, the heart rates tend to converge near the maximum heart rate of the people who were running. Oxygen saturation paints a slightly different picture, with the low and mid-speed runs providing minimal drop in specific oxygen levels, while the high-speed run had a strong impact on it, with the mask providing even worse athletic performance. In order to tell if these results were significant, a one-way ANOVA was completed using 2-key to determine if the results were significant within 0.5%. While a number of data points were near significant, such as the difference between different face mask performances, the only thing that was found with certainty to be significant was the heart rate between low and high speeds. This indicates that while additional experiments are required to fully understand the impact of various mask design features, our experiment was still provided some useful information as to the effects of wearing a mask while exercising.
pH extremes change the structure of the coronavirus E2 glycoprotein, inactivating the virus at pHs of 3 and below or 12 and above, as shown on the graph through the TCID50 assay. Hyaluronic acid is biocompatible and abundant in the skin, which means it can lower the pH of the mask and inactivate the virus safely. Electrostatic spinning forms a superfine polymer fabric by using a charged polymer solution and offers a great option for forming a hyaluronic acid fabric. Finally, an endoskeleton of the mask was generated to improve dead space, which is made of PETG that is biocompatible and waterproof for a final durable design. This overall prototype offers a new way to inactivate coronavirus particles with a breathable fit.
The next steps would involve designing and manufacturing the masks, where design constraints such as dead space, material type, addition of vent would have to be considered, along with manufacturing constraints such as economic viability, efficient mass production, distribution, and testing. Applications beyond COVID would also have to be explored in the future.
Finally, we would like to thank Dr. Stephen Wereley for working as our mentor throughout this project, Dr. Lindsay Bottoms for providing insight on designing the experiments, and the Purdue Honors College for providing financial support for this project through a scholarly project grant. Thank you for listening to our presentation on developing a performance face mask.